Hi guys, Justin again from chemistrynotes.com, and today we're starting a whole new section, it's like a whole new chapter, and this section is called Chemical Quantities and Stoichiometry. Now, you're going to hear the word stoichiometry a lot in the first semester of general chemistry, and it's on lots of quizzes and lots of exams. It's very important to know how to it's more important to know how to do stoichiometry than it is to understand kind of what the definition is. But the definition is stoichiometry is the area of study devoted to the quantities of materials consumed and produced in a chemical reaction. So basically, it's like if you have 43 grams of this starting material, how many molecules or moles or grams of this product will be produced. And we're going to do 4 sample problems at the end of this video that are really important to know how to do. They show up on quizzes and exams all the time. Okay, so section 3, chemical quantities and stoichiometry. Let's get started. All right, so I've given you the definition of stoichiometry. It's an area of study devoted to the quantities of materials consumed and produced in a chemical reaction. All right, now before we can get into quantities and stoichiometry and stuff like that, we have to give ourselves a little bit of background. So, atomic masses is my first subject here. In 1961, a system was devised to assign atomic masses to each element. To do this, we had to develop a standard, and we used an isotope of carbon, carbon 12. The nuclear symbol there is 12,6C, that's carbon 12. And we used this isotope of carbon as the standard. And we assigned an atomic mass of exactly 12 AMU. Okay? AMU stands for atomic mass units. So now we have a standard from which we can compare everyone else to. We have just literally defined carbon 12 as having an atomic mass of 12 AMU. Okay? Now, at the top of page 2 of today's notes, we have the following question. It says, so why is carbon's atomic mass on the periodic table 12.01 AMU instead of 12 AMU, like we just said? Well, the answer is carbon 12, carbon-12, that particular isotope of carbon, that's not the only way that carbon is found in nature. Okay, it's the most prevalent, but it's not the only type of carbon isotope. So here's the answer. Most elements occur as a mixture of isotopes, and natural carbon is found in the following variations. 98.89% of the carbon that's in our environment is carbon 12, but 1.11% of the carbon atoms that we would find in our environment are carbon 13. Okay, that's one extra neutron. So if we do a weighted average here, 98.89% times the 12 AMU plus 1.11%, written as a decimal of course, times 13 AMU, it comes out to be 12.01 AMU. This is an average atomic mass for carbon. So on average, any particular carbon atom is going to weigh, on average, 12.01 AMU. Okay? This is a weighted average of isotopes. Bear in mind, not a single carbon atom weighs 12.01 AMU. But on average, if you take a collection of carbon atoms, the average mass is 12.01. All right? And pretty soon we will ditch AMU in favor of a unit called grams per mole, gram/mole. But just one last note here. Note that not a single carbon atom weighs 12.01 AMU. This is an average weight. This is why atomic masses of elements are expressed as decimals on the periodic table. And generally speaking, I like to go to the hundredths place. So for example, the average atomic mass for hydrogen is 1.01 AMU. The average atomic mass for oxygen is 15.99 and a whole bunch of other numbers AMU. Okay, that's why they're found as decimals. They're calculated weighted averages. All right, new page of notes here. That was atomic mass. Now let's introduce something called the mole. Anytime I introduce the mole, I also like to bring up kind of the everyday kitchen term, dozen. We know that if you have a dozen eggs or a dozen slices of bread, that's 12, right? Well, the mole is kind of the same idea. Now, the mole, funny enough, is abbreviated MOL, which is just one letter short of the full word, but it's abbreviated MOL, mole, not to be confused with molecules. It's abbreviated MOL, and 1 mole of any substance contains exactly 6.022 times 10 to the 23rd items of that substance. Okay? As an example, a dozen eggs is 12 eggs. If I have 1 mole of eggs, I have 6.022 times 10 to the 23rd eggs. Another example, if I have 1 mole of iron atoms, I have 6.022 times 10 to the 23rd iron atoms. If I have 1 mole of bananas, you guessed it, 6.022 times 10 to the 23rd bananas. Okay? 1 mole of water molecules, 6.022 times 10 to the 23rd water molecules. So in the first example there of this particular one, iron, those are atoms. The third example, water, those were molecules. So Avogadro's number we often see in front of words like atoms or molecules. So 6.022 times 10 to the 23rd, as I just mentioned, is called Avogadro's number. And it's an important number to remember. Most of you will find that you don't have too much difficulty remembering that number. For some reason, it just sticks in our brain. 6.022 times 10 to the 23rd. All right, so we're at the top of a new page of notes here. Remember, we're just kind of building the foundations before we can start to do these 4 practice problems that are coming up in this video on the early types of stoichiometric calculations. Now here it says the mass of 1 mole of an element on the periodic table is equal to its atomic mass, or its AMU. So for carbon, right, the average atomic mass for carbon is 12.01 AMU. Well, that's equal to the mass in grams, 12.01 carbon grams divided by 1 mole of carbon. In other words, the shortcut is this. If you see something that says 12.01 AMU, or for nitrogen 14.01 AMU, you can replace the AMU with grams per mole. It's much more useful. Rarely do you see AMU except for when we first introduced this stuff. So we're going to go with grams per mole from now on. Okay? Here's our first of 4 examples to round off this video. Example, find the mass in grams of a sample of 6 iron atoms. Well, start with what you're given and put it over 1. Okay, when in doubt, start with what you're given and put it over 1. Also, when you're in doubt, go to moles. Moles is kind of the epicenter. From moles, you can go to grams. Okay, from moles, you can go to molecules or atoms. 6 Fe atoms over 1. Well, we have to get out of atoms and into moles. So down on the bottom, 6.022 times 10 to the 23rd iron atoms for every 1 mole of Fe. Now I'm in moles of iron. Well, for every 1 mole of Fe on the periodic table, it weighs 55.85 grams of Fe. You notice I include all the units. I'm not leaving any units out. I'm not just writing numbers as fractions. Very important because I need to follow the units. So you end up with 6 times 10 to the minus 22nd grams of Fe. Example number 2 of 4 for this video. Top of the page. Example. Find both the number of moles of atoms and the actual number of atoms in the 10.0 gram sample of aluminum. Okay? Well, I see that we only have 1 number in this problem, so I'm going to hone in on that number, 10.0 grams, AL, put it over 1. I need to go from grams to moles. So if I have grams in the numerator, right, then I'm going to divide by the atomic mass. 26.98 grams aluminum on the bottom for every 1 mole of aluminum. Cancel grams of aluminum, and you're left with the only units left are moles of aluminum. We started with 3 sig figs. Our answer is 3 sig figs. 0.371 moles Al. Okay? All right, well, now that I'm in moles of aluminum, I could have gone in one step to atoms, but I'm going to start from the beginning again. So 10.0 grams of aluminum over 1 divided by 26.98 grams of aluminum with 1 mole of aluminum on top. That gets me into moles of aluminum. For every 1 mole of aluminum on the bottom, I have 6.022 times 10 to the 23rd atoms of aluminum. My answer, 3 sig figs, 2.23 times 10 to the 23rd atoms of aluminum. Follow the units, right? The units are more important than the numbers. Example. Third example. A silicon chip has a mass of 5.68 milligrams. How many atoms are present? Start with what you're given, put it over 1. In this case, we're given milligrams. I've got to get out of milligrams. So I do 1,000 milligrams on the bottom, 1 gram of silicon on top. That gets me out of milligrams and into grams. Now that I'm in grams, I want to go to moles. I use the periodic table, follow the units. I want to cancel grams, so 28.09 grams of silicon's on the bottom, 1 mole of silicon on top. Now I'm in moles. One step left. For every 1 mole of silicon atoms on the bottom in the denominator, my numerator is 6.022 times 10 to the 23rd atoms, 1.22 times 10 to the 20 atoms of silicon. See how I'm just following the units? The previous numerator is now going to be the units for my denominator. Then I cancel. The last numerator in that left to right movement is my unit. Last example of this first video from section 3. Calculate the number of moles and the mass of a sample of cobalt containing 5.00 times 10 to the 20th atoms. Well, we start with what we're given. We'll put it over 1. So my very first term is going to be 5.00 times 10 to the 20 atoms CO. Don't forget to write CO, little o, right? It's not carbon monoxide. It's cobalt. Got to get out of atoms and into moles. Why did I say moles instead of grams? Moles is the place to go. Moles is the epicenter. It's the hub. Always go to moles if you can. For every 6.022 times 10 to the 23rd atoms of cobalt in the denominator, that's equal to 1 mole of cobalt. So I divide, and you should practice that to make sure you can do your division correctly on this. And I get 8.30 times 10 to the minus 4th moles of cobalt. Okay? Now, 5.00 times 10 to the 20th atoms of cobalt, and then I say, but wait. That's because I'm trying to save myself some work. I could have rewritten that expression on top and then continued with it, but I trust my answer is 8.30 times 10 to the minus 4th moles. Moles is a good place to start, so I just have to multiply by my atomic mass of cobalt, 0.0489 grams of cobalt. Started with 3 significant figures, I end up with 3 significant figures, 0.0489 grams. That first zero is a leading zero, right? 0.0489 is 3 sig figs. Okay, in the next video, we're going to introduce molar mass, which is it's just like atomic mass, but you add up all the individual atoms of a molecule or a compound. Okay, after we introduce molar mass, we're going to start to work more with stoichiometry. Stoichiometry, one of the most important topics in the first semester of General Chem. Stick around, video number 2 from section 3 is coming up next.